Hi, and welcome to 4.5 Applications of Linear Relations. I thought about changing the intro from G to R, given how much people seem to like word problems, but here we go anyway. So this whole chapter is on word problems, and I find part of the biggest problem people have with word problems, they really want to find one kind of way to do a problem and then memorize it and then want to be able to do that again and again and again. And the trick to word problems is, well, that's just not the case. So what you really have to do is you have to take a good read through the word problem, try and understand it, and try and figure out which ones of the tools that you have and know that you can apply to this particular scenario. So in this particular chapter, we've pretty much exclusively talked about slope. We've talked about two types of slope. We've given slope the variable m, and we've talked about how it's always going to be rise over run, which is the same as delta x, or sorry, my bad, delta y over delta x. And that's the same as y2 minus y1 over x2 minus x1. So all three of those different expressions can be used at different times. And since they're all the same, if you can figure out how to use more than one of them, they should always come to the same answer. We've also talked about both slopes and rate of change. We've talked about how the only difference between slope and rate of change is that slope is just exclusively numbers. So usually we'll just see a graph and there won't be any units at all, whereas with rate of change, the units then become very important. So let's take a look at example 1. I always find it's nice, if I can, to either sketch some type of diagram or picture with word problems. It just helps me sort out the information that's there. So example 1, an iPhone repair company charges a fixed amount plus an hourly rate to fix a phone. A 3-hour fix is $250, and a 1-hour fix is $150. So right away, I noticed that we've kind of got these two values that live together. A 3-hour fix is $250, and a 1-hour fix is $150, which lends me to think that maybe somewhere along the line I'll be using this form of the equation. The y2 minus y1 is equal to x2 minus x1. A, though, says use the variables T for total cost, H for hours, R for hourly rate, and A for the fixed amount. And write an equation, and apparently we're missing some words here. Write an equation that will predict the cost of fixing a phone. Cool. So we know that the total cost, so we're looking for an expression, the total cost, and it's going to be whatever that fixed amount is, as it says, fixed amount in is plus that hourly rate times the amount of time. And that'll be A, and that's all they're looking for. It's just in terms of variables, what that equation is going to look like. I've made a mistake because I've got T in there twice. That hourly rate, this second T is for hours. This one is supposed to be an H. How many hours times that hourly rate? B is find that hourly rate that we just talked about. So this is where I think it's useful to just sketch a little diagram. If we're ever graphing anything where it has to do with time, time is going to be along the bottom, and in this case it's in hours. And then the only other thing we're talking about is cost up the side, and that'll be in dollars. So I've got a 1-hour fix, and I'm just going to pretend that that's a 1-hour fix. So my x coordinate is 1, my y coordinate is 150. I've got a point there. And then some later time, 3 hours, it doesn't matter where we put it, but it's going to be higher. So my 3-hour fix is $250. So now I have two pairs. We can call this one 1 and this one 2, and I can use my rate of change formula, which is going to be a y2 minus y1 over x2 minus x1. My slope is then going to be 250 minus 150 divided by 3 minus 1. So my m is going to be 250 minus 150, I think, is 100 divided by 3 minus 1, which is 2. So m is going to be 50. And now this is rate of change, so we should have units. So I'm going to back up a step and go back here, and we're going to take a look at what I think those units should be. Rise, which is the top, is dollars. Run is the bottom, is hours, which means this is $50 per hour. And that is my final hourly rate. Find the fixed amount. So this is a little bit tricky. I think there's a couple ways we could go about it, and I'm going to go about it a fairly algebra-intensive way because I like to practice algebra. I'm a bit of a masochist that way. So we have this equation from A. T is equal to A plus RH. And I know from B that my rate is going to be 50. So I can go ahead and I can substitute that into my equation. T is equal to A plus 50 times the number of hours. And what I can do next is I need to find a point. So I'm going to use this point, my 150, and I know that for the hour, if the hour is 1, then the total amount is going to be 150, and I can substitute those expressions into my equation. So T is 150. A is what we're looking for, that fixed amount, plus 50, and my H is 1. And now I have an equation with one unknown in it. I've got one variable, which means I can rearrange my equation and find out what that variable is. I'm going to start by simplifying because I can do that here. 50 times 1 is just 50. I have 150 is equal to A plus 50. And now I'm going to have to do some algebra. I'm going to have to rearrange this equation and try and isolate A. All I have to do is remember what I do to one side of the equation, I must do to the other side of the equation, and I must remember my BEDMAS rules. So in this case, I'm looking at this and I'm like, oh, I got to get A all by itself. I want to get rid of that 50. In order to get rid of a positive 50, I can subtract 50, because positive 50 plus negative 50 is 0. 150 minus 50 is 100, and I get that A is equal to 100, which means that fixed amount, A, is equal to $100. And that will be C. Let's scroll up and take a look at what D is. Oh, D is the domain and range. I've taken a look through this textbook and I've looked at what the answers are. And while domain and range is important, and I like the ideas of the way they've presented the answers in the key, I'm not going to find these questions particularly useful. I think they're going to lead you astray for the longer run and cause more confusion than help. So anytime for 4.5, it's asking us to find the domain and range, you could just go ahead and choose not to, would be a lovely. Example 2. An old car is worth $7,000 now and will be worth $3,000 more in 5 years. And then we're going to answer some questions about that. So this one's a little bit trickier, just in the statement. An old car is worth $7,000 now and will be worth $3,000 in 5 years. So $7,000 now is one of those ordered pairs that we're talking about, and $3,000 more in 5 years is close. So again, if I do a little sketch of the 2 points that they've actually given me, I haven't even read the question yet. I'm just kind of thinking about the information they've given me. We've got time, and this time it's in years on my x-axis. and I have the worth in dollars on my y-axis. So time right now, we'll call that 0. I'm up at like $7,000. So this point is 0 in time, 7,000. And then at some later time, 5 years, it's going to be worth $3,000 more, which means that it's going to be 3 plus 7 is 10,000. So I can actually look at this, if I go back and I go A, determine the annual change of the worth of the car. So I can look at this two ways now, given the information they've given me in this question. I can look at it and I can say rise over run if I would like on this one. Because I know, sorry, I just did a little typo there, rise over run. I know that my rise is going to be $3,000 if my run is 5 years. So I get this expression here, $3,000 in 5 years. Now, if you'll excuse me just for a second, I might have to figure out how to, oh, there we go. I'm going to have to plug that into a calculator, 3,000 divided by 5 because I'm bad at the mental math. I should know that one though. It is $600 per year again. Same as last time. My rise is in dollars. My run is time. In years, it's $600 per year. I can also look at this and I could do my y2 minus y1 over x2 minus x1 if I wanted. I have 10,000 for my y2, I'll call that 0.2 and that 0.1, my 10,000 minus 7,000 divided by 5 minus 0, and I end up with 3,000 divided by 5, which is going to be $600 per year. If we do two different things, two different ways, and we come to the same answer, chances are really high we did it well. Either of those approaches will work well with this, and they get the same answer and are essentially the exact same thing. B, write an equation that shows the worth of the car depends on the present value, the years, and the annual change. C, I tried to put brackets around that earlier, but I kept turning it into a copyright symbol, so I'll add those now. B, so the worth of the car is going to depend on how much it's worth now, time, and how much it changes. So how much it's worth now is going to be its present value. It's going to be very similar to the previous one, where I take the annual change and multiply it by the amount of time in years. And we should do a little bit of a sanity check. If I plug a t in for 0 right now, if I'm like, okay, right now, then it would be worth the present value, which is $7,000. So this equation seems to work logically, and it is definitely the one we're looking for. C, show the equation B with the known numbers substituted in. I'm actually going to rewrite that one. What I actually want to ask is, let's get rid of that. Substitute misspelled that as well. Substitute in C and P, which is the present value and the annual change. Because when I do that, I end up with this really nice equation where my present value is 7,000 plus my change, which is 600 times t. I end up with this really nice equation that now, given any time at all, I can find out how much this car is going to be worth, which is super convenient because D asks us how much the car is going to be worth in 2 years. So now time is going to be 2, and I can we're looking for how much it's worth, and I can take that and I can substitute it into this expression, 600 times, not a t, because we know that t is 2, which I think is $8,200. Give me 1 second, and I will check. 7,000 plus a 600 times 2, $8,200 on the button. E, again, I'm going to have to scroll up for a second. E, how much will the car be worth or how much would the car be worth 3 years ago? So how much would the car, that's a bit. Would the car be worth 3 years ago? So 3 years ago, so this time we're looking for the worth again, but in time is 3. And notice how if I just plugged it in as a 3, that would be 3 years in the future. So in order to look in the past, we can put a negative sign out in front. So our W would be equal to 7,000 plus 600 times negative 3. And again, I think you guys should be doing it too. When I pause to plug it into a calculator, it should give you guys enough time to plug it in too. And we know then if we both get the same answer, just like the one above, we should both be right. And if we don't get the right answer, one of us is making a mistake. If you've been in my class, which should be just about everybody watching this video, you know that in fact, I make mistakes. And that looks like we're going to final answer, $5,220. And I think that was the last question. So let's look at example 3. I'm just going to change my view and see if I can get a bit wider. Yeah. In 2018, the Dead Sea was 306 meters deep. It dropped 6 meters over 4 years. What will the sea level be in 2 years? What was the sea level 6 years ago? And when will the Dead Sea be dry? So this one doesn't give us a whole lot of step-by-steps. It just jumps straight into the questions. So from the previous example, what we did was we made an equation. So if I think about this, maybe I should define my levels, or define some variables. So the Dead Sea is 306 meters deep. That's how deep it is right now. So let's call that D. How deep the Dead Sea is. It drops, so let's call that our rate, is a rate of how fast it drops, rate of sea level drop. dr, t, let's call that time in years. And we're going to need one level for the future level of the sea. Let's call this the future sea level, or let's just call it sea level. So if we're making our equation, our sea level would depend on what it is now plus the rate times, sorry, not an L, times the amount of time. So I've got that exact same equation as I've been making before. So what I'm going to have to do is how deep the sea is. I can substitute in that value, and then I need to find the rate. So my rate this time, I think, is easier just to look at rise over run, because I know that it goes down 6 every 4 years, which is, if I want to reduce, as I should, a negative 3 over 2. So that I know the sea level is going to be 306 minus 3/2 times t. And then I can answer A and B really easily, because I know that for A, my time is going to be 2, and I'm looking for what the sea level is. So L is equal to 306 minus 3/2 times 2. If you want to type that in as 1.5 into your calculator, that works too. It might be a little bit easier. I'm going to plug it into my calculator again because I've got that 3/2 in there, which makes things a little bit tricky to do in your head. Although I think I just figured it out. I think it should be 303. Oh, I should have done that one in my head for sure. Someone's laughing at me out there. 303 meters. For B, the question is, what was the sea level 6 years ago? So time is going to be -6, just like the previous question, and the level is what we're going to be looking for. So our level is 306 minus 3/2 times -6, which I think L is then going to be 315 meters deep. Double check that one for me in your calculator. I did it pretty quick in my head, but that should be 3 is 9, 9, and 6 is 15. I'm pretty happy with that. So C is going to be a little bit trickier than those previous two. C is asking, when is the Dead Sea going to be dry? So our time is what we're looking for because we're looking for a when. And our level, well, when it's dry, it's going to be down to 0. So our L is going to be 0. And maybe I'll just write this whole equation out first because it's pretty high up my screen right now, and I keep forgetting to look at it. The 306 minus 3/2 T. L is going to be 0. 306 minus 3/2 T. Okay, so now I've got some algebra that I'm going to need to do so that I can isolate T, and then T will be how much time. So again, to get T all by itself, I'm probably going to have to move this 306 first, but it doesn't really matter. Yeah, let's move the 306 first, just so we can be consistent. I have a positive 306, so if I subtract 306 from both sides, -306, what I end up with on this left-hand side is -306, and on the right-hand side, if I combine like terms, I've got a positive 306 and a negative 306, and that's 0. So I'm left with a -3/2 T. What I can do to both sides of this now is I can multiply by, I want to get rid of the -3/2. So I'm going to multiply by the reciprocal, which is -2/3, and I have to do that to both sides. My negative times a negative is a positive. 3 divided by 3 is 1. 2 divided by 2 is also 1. So I'm left with T on one side, and I've just written it on the other side because it doesn't really matter what side the equal sign on, and I like my variable on my left-hand side a bit better. And I am left with 204. So now we're back to our critical thought area again, and I want to ask myself, does 204 make sense? When is that? Well, if we scroll back up to our original question, our starting year was 2018. So when will the Dead Sea be dry? 204 doesn't really answer that. But if we know that we started in 2018, then the year is going to be 2018 plus 204. Again, plug it into your calculator if you'd like. Practice doing some mental math if you'd like. If you do it at the same time as I do it, then it seems a little faster. We get 2,222. So in the year 2,222, it will be dry. And that concludes this lesson. If you have any questions, feel free to reach out and send me an email, send me a message, or make an appointment on my Google Classroom. Other than that, I hope you guys are having a wonderful time, and I will see you again soon.